Hey guys, Mark from 42freeway.com. We got some solid information from the Department of Transportation on the wall collapse, the road collapse in Bellmawr, New Jersey 14 months ago for the Direct Connection Project. This is an engineering analysis document. Basically, before they can answer the questions, we really want to know how long this is going to take, how much money. They needed to know why it happened, why it failed, so that they could learn from it and not repeat those same problems. So they do give some recommendations. Hey, this didn't work, and if you'd have done this, but it's definitely not the full plan. I've done this video 100 times. I have a version that's an hour long. I'm trying to get this down to like 20 minutes. So hang with me, guys. We're going to make this fast. All right, so this is the 295 South roadway. It was not in use at the time, but you can see what happened here is there was the underlying subsurface pushed out, carried the wall with it, and there was a severing there. This project is in Bellmawr, New Jersey. Here's Browning Road. This bridge is being rebuilt right now. This is 76 to 42. Philadelphia and Camden's up this way. Atlantic City's down to the bottom of the image. And what we just showed with the failure in the roadway, this is the new 295 South right here, and they denote it as wall 22 in the documentation. They see this project as 3 sections, or the document sees this as 3 sections. This sort of gives some highlights of why this thing failed, and we're going to talk about the key failures in one more slide, but they break this out into 3 sections. The Msc, mechanically stabilized wall and retained fill. So this is the square concrete wall out here on this side. The cemetery's over here. This whole segment with the wall, its support steel bracings, and the dirt is one section. The slope here is actually a sand slope. So all the embankment here and even under the wall, there's a hint, guys, this is all sand. And then the third segment, which I don't think I've spoke about, it's probably new to most of you guys, the CSES, column supported embankment system, that is two facets. The LTM, load transfer maps, horizontal mats that sort of go out in a broader area to capture load above it. And then columns. These are actually, even though they're depicted shorter here, they're probably 70 feet long. Columns that go down, so they capture the load on the mats and transfer it down to these columns to go to a lower level. This report was actually done by Hardesty Hanover. They are not part of the Direct Connection Project. When the failure happened, the Department of Transportation wanted a sort of third-party group to analyze it. So this H&H, I'm going to say H&H because that's how they call themselves for the rest of the document. They are engineers. They build roads. They do all this stuff. So they were perfect people. They talked to everybody, all the contractors, the design folks, did their own they literally tested everything that went into designing the plan and then stopped to think, how are the conditions actually, at the time of the failure? Let's rerun the calculations with that. So they open up their doc basically with an executive summary with, I think it's 4 bullets, and then I add a couple. The I-11, L11 sand material used was not an appropriate material to support the wall, and when moisture was, the moisture conditions changed, it just made it even worse. There is a place for sand in projects like this, and we're going to learn that as we get through the slides, but it needs to be contained. And the fact that this was on a slope, gave the pressure and the dirt an escape route. The CSES, that lower level area, used unreinforced concrete columns, and they were not adequate to withstand the vertical and horizontal loads. I mean, some of these things actually sort of fractured and sheared, and they should have been able to hold up better to movement. The project site is known for, they use the word chronic, high groundwater conditions. A lot of research went into that. Basically, the water went higher than some of the early expectations were, and a lot of the engineering design concepts were based off a much lower water level. And the heavy precipitation, the day before, actually the whole week, I think it rained 3 or 4 days out of the week, exasperated the problem. The roadway should survive this, should stand it, but I think it's more of a straw breaking the camel's back. It's why it collapsed when it did, because so much water had hit. When I say 42 Freeway ads, for the most part, all of this, the text that you're going to see is right from the report. I didn't want to confuse that aspect, even though I'm just giving my own verbal opinion here. But I know some of you are going to watch the first 3 minutes, so I said, let me throw these bullets in. Per the contract plans, the wall was not detailed to extend down. So as we'll see it again, but you have the wall, you have sand, and then you have that lower level substructure. Basically, they say due to cost. The vertical load-bearing aspects had sand and then an exposed slope. So not only did you have the sand there, the sand was not contained. We're going to talk more about that. Whoops, hit the wrong button. Groundwater was not taken into account for some calculations. I just spoke of that. and 3. The MSC, the top part, one of the most visible parts, and it's, people see it elsewhere, the concrete vertical panels, basically was designed within contract specifications and wasn't really at fault here. It was what it was sitting on that was the problem. All right, so this is just another depiction of the side slice. It shows some of the vendors here. South State Inc. is the main SSI, the main construction folks, but someone else designed the Msc wall. That's the Reco company. Dewberry was the engineer. I think they're the engineer of record for the whole project. And then there's the CSES embankment system. That was by Menard. Visual observations. This is just basically saying the dirt pushed down and out. Maybe this is a better depiction. Down and out. If you remember that image, and we'll see it again, how the yellow soil came underneath the wall. It allowed the pressure to escape that way. Just another version. Basically, this is showing the black is as constructed, 9-foot vertical space here, the slope. The red is after the collapse. It divoted that much, 12, almost 13 feet drop. And this is the vertical wall, and that's where it rested. And then what it did is down and out. It literally just pushed the soil up and out. First thing they got to do is, first make the property safe so it doesn't continue to slide further into the roadway below it. But also, get in there and see what's going on. What caused this failure? So H&H came around. It's probably within the week. They were out there when they were doing the deconstruction, and they were there for 6 weeks, is what I saw. Basically, this is the before, like right after the collapse. And then this is, weeks later, just to show how much they removed. We have some other pictures of that. Step 1, make it safe. Step 2, let's get in there and see the panels, the Msc panels. Was there any failure in there that caused this to collapse? Step 3 was, hey, let's dig in there deeper. Let's get a look at what the LTM and those columns, those subgrade, support columns did. This is them taking the wall apart. This is without the panels. This is, showing how wide they went. I think they later on then kind of came back a little bit. Throughout the whole process, they did, H&H tested everything, water, soil, compression, strength, I don't know, everything was tested. In fact, I'm probably repeating myself, even when they looked at the design documents, they were based on facts and figures of, the water level and different things. They recreated all those and then said, okay, what's different about the project today in the area today? Let's do those variations. Just another depiction again, just to show, hey, this was here and it pushed through, and that's why you saw the bulging, and that's why this wall shifted down. This is, some of the horizontal LTMs. It's a geosynthetic, I think is the term. And basically what they're saying, it was displaced and sheared. There's a diagram that actually shows how much more radical this is. You can see the angle here, maybe over there a little bit better, angle, and then those are separate. This is interesting. This is the column that goes. So we're below the grade, right? So you got that horizontal piece. This is the column below. Note the threads that are in it. And here's an example of a failed column. So it has threads. This one's sheared. Look, there is no sort of steel rebar going through that. That's just 70 feet of concrete. We're going to talk about more about this. Another example of them doing testing. I mentioned 30 feet as a value that was used for some of the calculations. At least one of the calculations that was important. Well, here we are. This is the wall. At 27 feet, there was freestanding water. At 47 feet, you could see moisture coming through the side here. And then at 57.5 feet, it was wet. Almost double. 0 to 30, 30 to almost 60. Almost double, the moisture being in there. Deconstruction Summary. So again, it appears that the slope and the underlying CSES elements shifted outward first. Some guy did a video like a year ago, 42 something, where he said, hey, that slope was not designed in a way to hold back the pressure, but we'll get to that in a second too. And then even the CSES on the lower level shifted. Portions of it shifted out, and we had shearing, multiple fractures, signs of shearing, the columns, the LTM. This is just another depiction. Oh, this is the one that shows how that LTM had shifted so much. So first off is this green leveling pad under the wall when it was originally constructed. This is where it ended up afterwards, probably 10, 12 feet away. This is a horizontal, was supposedly originally a horizontal LTM. You could see the angle on that and how this shifted place. So the wall area technical reviews coming up. Basically, there are 4 contracts. We're in contract 3 right now. So contract 3 is probably the most significant sort of new 295 contract. 1 and 2 were sort of the prerequisites. The Bell Road Bridge was rebuilt. The Creek Road Bridge was rebuilt. All those things had to be done. The Creek Road Bridge, down by the Wawa, that is, had to be done first. And contract 3 is a big one. We're going to talk about how contract 2 had some work done that impacted the collapse. What this is showing here is the ground level goes across here, this red line. And in contract 2, they literally dug out, I think it was 30 feet. I actually read that, dug this out. And this is going to get a little bit more significant. And then what they did is after they dug that out, they had to rebuild on top of it. Even during contract 2, there were already earth failures. Here's another side shot. I remember seeing, even later on, when they had the wall going up, and they had much larger landscaping stones there, which I remember saying that was stupid because eventually there's all grass is going to grow between them, and who's going to take care of that? Those stones slid down. This is a very look at the size of the depressions there, distressed ground. This is literally the segment where the collapsed wall was built over top of. Now, of course, they fixed this, thought they had it fixed, but even after they got some of the panels up, maybe 2 or 3 rows, look, they're saying this is the ground. This is water seeping through. So it looks like up here it's dry. It looks like dry conditions. Imagine a lot of rain. This groundwater line goes higher and higher and higher. The more water you get into that soil becomes, the strength decreases. Another facet here is when they did that cutout in contract 2, what it did is it dug them down into lower level. In Deffert where I'm at, you go 6 inches, you're hitting clay. And the water just doesn't move down. So they dug this out, remember, to build it up a little bit, but then they replaced it with sand. So what ended up happening is they sort of created some subterranean passageways for the water to flow, both at a higher point in the wall, and then when it hit the wall to slide down the wall. So this is even before the construction. They're showing water. Here's during contract 2, collection of water. Well, maybe that's just from the rain, but look, it's all pretty dry up here. They already have some panels going up, and this is very clearly water seeping. Now, to be clear, this is not just water sitting on the edge. The water is through the entire mountain of dirt, and it's just, this is the parts that's able to seep through, but there's water all through that. So again, just another depiction where they're saying, hey, the water seepage is observed at slightly lower elevation due to construction activity. Previous history involved the excavation of the upper Woodbury clay. So they dug this out, which no longer extends to the face of the slope, and was replaced with sand. So they put like a sandy surface here, which is, as you can see, the slope here. So, actually, you could see, there we go. You could see the original contract 2 line, and then this is what they replaced it with the sand. Wall area technical summary. I bolded this in other parts of the presentation, but I'll just buzz through this. The wall was constructed over sand. The contract 2, removing that clay, just changed the substructure there and just made the subsurface like a bad thing to build on top of. The slope material was wet from the moisture going higher and higher, and it just kind of reduces the structural integrity of that soil. And then there's a thing about this last bullet here, just the strength is measured, and the clay actually gave a variable strength to some of the soil materials here, which in some of the calculations they expected a consistent, like a number that was in the middle of the value. Design and construction, here's the 3 elements. Wall 22, retained fill. Typical wall, here's those square MSC panels. This is sort of the steel fingers going into the dirt. This system works. They're basically saying that this system did not fail. What failed is what is below this. That was just some federal things. Would function satisfactorily if built on stable ground. So basically, Rico is the company. They designed the MSC. SSI installs it, but I think Rico not only designs it, but I think they build the panels themselves. And in their document, they said, hey, this would function satisfactorily if built on stable ground. And the document assumes that others would be responsible for design of the lower level. That's a common thing. When if you're a framer for a house, you're hiring someone else to build the concrete block basement. You want to know that it's safe and it's done, but you're relying on their engineering. If the wall blows out below the house into the basement and your wood frame crashes down, people driving by are going to say, wow, that wood frame failed, but no, reality is it failed below it. Moving fast, just to call out, apparently for back in February 2019 there was an install issue with some of those panels that was addressed and passed everybody's criteria. They do call it out here. I think it makes it into a bullet, but then they don't really tie it back to being anything significant to why things failed. So the Mse Summary. So remember, there was 3 things we were reviewing, 3 core construction areas. So this is the Mse, the first one. The wall design actually followed the standards, the procedures. It was done good and fine. There was also excessive lateral movement of the wall, during the construction, which doesn't really, that's probably the only time it gets mentioned. The second part is the slope design. If you remember, this is the sand here. And part of the forensic study corrected an independent slope study analysis of the slope supporting the wall. So they replicated all the original tests and said, okay, you know what, solid, good job, guys. They said, all right, well, let's redo this, but let's consider that we found groundwater as high as 44. They based everything off a slope elevation of 30, but we saw it at 35 and even 44. They also retested the strength of the fill material. This is what is called a 2-layer foundation soil system that they believe they were trying to implement here. So basically what it's saying is you can even have a weaker sand substance here, but as long as it's contained. So basically this is saying either a completely flat surface, so basically the earth next to it is containing it, or just containing it some other way. A pile of sand, if I stood in it, it's going to slide and fall, but if I put it in a bucket and stood in it, it's going to hold me, right? So that's basically what this is saying. Trying to give myself a pat on the back here. A year ago, within a week of the collapse, I put my own video up, and I basically drew some scenarios here where I'm like, look, a truck rides on the ground, and when it's flat and there's earth there, it doesn't sink because the dirt can't shift out. The second image they present, this one's going to be real interesting, is here's the wall, here's the pressure coming down. It's supposed to be held in here between the CSES system and up here. But since you have the sand off to the side and it's not contained, you're giving a release valve for the pressure to push the dirt out. So you have the red arrows. This is from the H&H report. Now look at this. 12, 13 months ago, I did a very similar diagram. Of course, mine's inverted to the other way around, but here's the road, here's the fill, pressure going down, going up, and I'm saying no pressure holding back. In my commentary, I literally say this exact same thing, like, hey, if this had been flat, think about this. When they come up with a new design, they could actually extend this wall all the way down to the lower level grade and not have a slope. They probably went with a slope to save a heck of a lot of money on the Mse wall. Just a thought, guys. No, here's the slope here. Imagine if this went all the way down. Well, then you'd have all of this dirt to help hold back the force of the pressure. This is my corny thing. I did a depiction of my house, putting a hot tub next to the house, and the local inspector guy said, hey, before I approve this, you need the engineer that's going to tell me that the weight of this, 8 pounds per gallon of water times 400, 500 gallons doesn't push through your wall. And it's funny that the local inspector caught this aspect, but you would have thought. All right, Msc Summary, a lot of words here. 2-layer soil system is applicable only for a flat surface or when it's contained. Soil's in the bucket. Soil placed over unstable ground condition. We talked about that with the contract 2 and the clay. Made it, the slope stability check was warranted during the design phase. They're basically saying it's in some aspect when they were designing the project that they didn't consider all the factors, like maybe the groundwater being in a different position. I think there's some more slides on that. Test results indicate the sand material strength decreases as the moisture content increases. So as you get more moisture and as the moisture goes higher up in that sand and fill, it actually decreases the strength of what it's trying to do, and it can cause things to start sliding. That being said, the material, that sand material, actually meets the standards of the Department of Transportation. It's just it wasn't maybe not implemented properly. It wasn't contained. Going back to the first bullet, I'm pointing like you guys can see my screen. The first bullet, it needs to be flat, needs to be contained. In this case, it was not either of those. Ground improvements, third segment here. This is the lower level, the LTM CSE. The columns are unreinforced concrete. The LTM is a geosynthetic, multiple layers of geosynthetic. This is sort of a diagram for so the federal government gives some sort of recommendations, but they don't review, and they gave money to the state to design this project and be involved, but they're not dictating how things should be implemented. The federal government does call out, hey, a steel and concrete column is going to be able to handle higher capacities of load, but it's more expensive. Similarly, the horizontal LTM, if it's reinforced concrete structural mat, it's going to be able to hold more, but it's going to cost more. In the case of the direct connection move, I'm not saying it's even needed, but they did not use the steel reinforced for either the LTM or the columns. This is just some of the checks they did. And get some more of the checks just to make sure everything works. So this is interesting. Initially, the columns were specified as a 15.6 inch and a 17.8 inch column, and it also says that the design of this thing, the recommended geogrid layers appear inconsequential in transferring most of the embankment wall 22 low ceiling icing. Basically, they're saying what's happening up here doesn't ever really get down to be to hit the down here because of the way the slope is designed. So remember this 15.6 and 17.8. During the design of some part of the project, the Menard company comes back, who's designing the lower level of the CSES, says, hey, you know what? It says 15 and a half, it says almost 18. How about we go with a 12-inch column, but it's going to be a threaded column. So what that means is, you can see in the image here, it's being threaded. The surface area, the adhesion to the soil around it, it's going to be greater, even though it's thinner. They also have an interesting idea here. The way they do this is, it's not like, if you build a deck in your backyard, you got to put those tubes in, the sono tubes, I think they're called, and you got to pour, dig and pour. They have this auger that goes down the 70 feet, but it's hollow in the middle, almost like getting a needle and the medicine comes through. The auger goes down. When it hits the lowest point, they pump the concrete through the hole, and then they back it up. And it's just, it's a grout concrete. There's, because of the structure, you can't put any sort of steel rebar. When they built the support columns to hold up the elevated roadway, you could see they built like a thick steel rebar in those columns. It increases the strength of the concrete immensely. They don't have it for these subterranean columns. So they did check all of the Menard's analysis using all the original known things, the groundwater levels. They say, hey, good, you guys did a good job. But then H&H said, hey, let's consider that the groundwater wasn't what it was. Ended up being higher than what was originally prescribed. So Menard's design analysis assumed a uniform groundwater level at elevation of plus 30 feet. This is right from the document. I didn't write this. H&H said, though, with the failure, they saw plus 44, plus 35, depending on where it was located on the wall. So they reran all the calculations based on that. The in situ is the original, means original, I guess. And they're saying that the shear strength varied. I think it was related to the slope and the drainage. That it was actually a varied depending on what part of the project you were on. And Menard used a consistent 1294, like sort of a middle of the road value there. And the columns going down, there's no reinforcement. It's just concrete. So there's another comment later on where they bring this up. There's just, by having the concrete in there, or even just some other structure, I don't know, fiberglass. That's what they do for the pool concrete. It gives it more flexibility, more ability to withstand movement, and then also just being significantly stronger. So they used the shear capacity was less. Oh, so here's an interesting. This is it. There's actually values. I should have bulleted these. Without that reinforcement, they're saying H&H that it's a 4.2 kips, some measurement of strength. Menard used a 6.92, like a 50% difference almost there. So they also, then this is really cool, they not only did they recreate the model with a computer program called Plaxis, they recreated a chronological series of events. What it was before they started the construction work, what happened with the cutout from contract 2, blah, 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 blah. And this is the image they got. Look, here's the wall shifted, here's the collapse of these columns. So, just a reminder, here's the broken. I don't know what this means when they go to rebuild this thing and fix it. Like, are all these broken pieces of concrete like scattered every 7 feet throughout there, and they have to dig that up? I don't know. Ground improvement summary. So again, the would be. So this is important. The CSES would satisfactorily perform if the sand slope is stable. So that was based on the original assumptions of all the other factors of groundwater and everything. So the design submissions failed to consider site-specific soil conditions, elevated groundwater conditions, and the strength reduction factor for plain concrete. That's actually like 4 bullets on its own right there. Didn't factor in the soil conditions, didn't factor in the higher water, and didn't factor in the plain concrete elements. It calls out here that while it doesn't give a percentage of better performances, hey, if you used a different column type, it would have held up better. And this is interesting. 88% of the vertical load to the underlying went to the compressed soils, not to the columns. Just in the way the LTM was designed, I believe what they say here is that it's, if they used more layers of the geosynthetic material, or maybe even like a concrete-based one, it would have captured more of that pressure and pushed it down through the more load to the columns. It says right here. The unstable ground condition was created initially occurred during the contract 2, and just straight up saying, hey, the type of column used in the CSS in these unstable ground conditions was inadequate to withstand the forces when the failure surfaces passed through. Maybe they're kind of saying, hey, this happened right before the contract, but I think all that was designed right. Anyway, I'll let someone else make that determination. The cement. Again, the cement column is unreinforced with very limited flexure and shear capacity to withstand a lateral loading thrust when applied project loads. Another thing is there were early signs of this. This is 14 days before. Look at this crack here. Basically, the rain was the straw that broke the camel's back when the whole wall slid. And then what we end up doing is just repeating the part in the beginning, which was the executive summary, which is just another repeat. And that's it. Did I get this under 30 minutes? I think I did. I literally shaved this in half. I moved really fast. It's the best I can do. I've literally been working on this for like a day and a half. I've done this so many times. Guys, thanks for reading. Thanks for watching. Thanks for supporting. Thank you to the H&H company. I already forgot the name, for putting together an awesome document. Your team did a great job. And thank you to the New Jersey Department of Transportation. I mentioned in the prior video, I did an OPRA request, public records request, to get this report. Somehow I messed it up. And then the Carrier Post got it before I did. Department of Transportation, you guys helped me out get this in a timely manner, though, after I realized my mistake. So thanks, guys.